So in this unit is all about energy, and we're going to talk about the different types of energy, energy transfer, how do we quantify and measure this energy. But before we start talking about energy, we need to lay a little bit of a foundation first. And today what I want to talk about is I want to talk about work. Now, last summer, my wife and I moved from BC to Calgary, and that was a lot of work. We had to pack up our entire apartment. We had to load it all into a moving van. We had to drive that van from BC back into Calgary. We put everything in storage. We moved in with our in-laws and my parents for a little bit. And then once we finally got a house, we had to go back to storage, pull everything out, move it all back in. It was a ton of work. And we throw this term around a lot, work. You work hard in school. You work hard at the gym and in the weight room. You work hard on your sports or your art or whatever it is. We throw that term around work a lot. However, work takes on a little bit of a different meaning in physics. I want to paint this picture for you, and we'll work our way backwards to figure out why that is. If I were to pick up a box, one of our moving boxes, I am doing work on that box. However, if I were to push against the wall, I'm not doing any work. Even though I'm exerting a lot of force, I'm not doing a lot of work. I'm not doing any work, really. And so that comes down to the definition of work. Now, one definition of energy is that it is the ability to do work. And so for us to understand energy, we need to understand work. Now, we define work as the transfer of mechanical energy from one object to another. And so what I think is that I think it's helpful to take a look at the formula for work to understand why lifting a box is me doing work on that box. However, me pushing on a wall is not me doing work on the wall. So let's look at the formula to discover what exactly is happening here. So let's go over to the iPad here. And so here we've got the formula for work. It reads like this. It reads W is equal to F times, that little triangle means delta, delta D. So let's break that down. First of all, the W should be pretty obvious. The W is equal to work. And we classify that, the units that we give that is J, or joules. And we'll talk a lot more about that because this also happens to be the unit for energy as well. So work in joules, our F is equal to a force. Now, we measure that force in newtons, N. That is our measurement for force. And then finally we have this delta D. Now the D stands for distance, but what that delta, that triangle sign means, that triangle sign means change. So this is our change in distance, and we measure that in meters. And so what we find out from this formula is that whatever we're applying force to actually has to move. It actually has to change distance for work to happen. So let's look at a practical example that you guys are going to be doing as part of this assignment for this week. So this is the type of problem that you would be given for a work type of problem. It's going to be very simple, very similar to this. So let's read it out and let's take a look at it. It says you exert a force of 25 newtons on your textbook while lifting it to a height of 1.4 meters to put it on a shelf. How much work did you do on your textbook? So let's break this down. The first thing we want to do, we know this is a work formula, or a work problem. So we're going to write out our work formula. We're going to say work is equal to force times distance, or you could also write it as equal to force times change in distance. Either way is fine. Now, we got to write out what we've been given. So first things first, do we know what the amount of work that was done on the textbook was? Well, no, that's what it's asking us for. How much work did you do on your textbook? So this is a question mark. This is what we're going to solve for. The next thing we're looking at is force. Do we know how much force was exerted? Well, right here, it says, yes, you exert a force of 25 newtons on your textbook. So our force is 25 newtons. And then finally, we got to look at distance. Well, our change in distance, it got raised up 1.4 meters. All right, so we write that in there, 1.4 meters. These are all the correct units Okay, we want it in newtons, that's good. We want this one in meters, that's good. So now what we can do is we can plug it all into our formula. So we know that work is equal to force times the change in distance. We know that work is equal to the force, which is 25 newtons, times 1.4 meters. We write it out like that. And so what we get, we punch that into our calculator. So 25 times 1.4 is equal to 35. Now, I'll write this two ways. 35 Newton meters, Newton times meters, which is the same thing as 35 joules. Now, the final thing that we have to check from our last video that we just talked about is our significant digits. So we go ahead, we count our significant digits here. We've got 2 significant digits in this one and 2 significant digits in this one. So we are just fine to leave it as 2 significant digits for this guy. And so this answer of 35 joules is our final answer. So a relatively simple problem. We could give you any one of the 3 things on your problem, any one of the 3 things, force, distance, or the amount of work in joules. We can give you any one of those 3 and ask you to solve for the other one. All right. So you're going to see a ton of practice questions in the assignment that I've given you. They're relatively quick and easy. You just got to be able to rearrange your formula. So while I don't want to spend a ton of time talking about the math side of it, the other part of understanding this work formula that we need to understand is we need to understand the graphical representation of it. And I think this is a good place to start because we are going to use graphs like this a lot. So what I have here is from our textbook, I have this graph. Now you'll notice that on the y-axis here, we have our force in newtons. And on our x-axis here, we have our position or our change in distance, our change in placement. All right. Now, what this graph is showing here, that is, it's saying that we have a force of 10 newtons. This line right here, this horizontal line, shows us a force of 10 newtons. And that force of 10 newtons is acting upon an object, causing it to move from its starting point here at 0 over 4 meters. All right, this is a force versus position graph. All right, now if we wanted to calculate the amount of work using this graph, what we're looking for is we're looking for the area underneath this graph. This whole square here, or this whole rectangle, is what we're looking for. So the shape of this is important, and this is what I want to talk about here. The shape of this guy here is a rectangle. And so, to find the area of a rectangle, that's what it's showing right here, the formula for an area of a rectangle is area is equal to length times width. All right, simple, not complicated there. If we were to substitute in what the length of it means and the width of it means, watch what happens. So for length, what I'm going to do is I'm going to put in this one here. And I'm going to say our length here is our change in distance, all right? That's our position. And our width here, I'm going to put in here our force times our force. Notice this is the exact same formula if we rearrange it for work, right? Work is equal to force times change in distance or change in position. This formula is the exact same. So when we multiply our y-axis by our x-axis, getting effectively the area underneath, we get our amount of work that's done on it. So let's plug in these numbers here. Our force that we applied 10 newtons of force, and our change in position, our change in displacement was 4.0 meters. We multiply those together and we get 40 Newton meters or 40 joules. Significant digits, we do a check there. This is 2 significant digits, 2 significant digits. So this is our final answer here, 40 joules. Now, this is great, and we can use this for a multitude of different applications when we're graphing it and representing it visually. However, what happens if the graph that we're using is not a perfect square? So here's another example that I brought in. Notice the graph is identical in the sense that we have force here on the y-axis and we have position here on the x-axis. Exactly the same as the last example, except something's different. Now we are increasing the amount of force over the course of that position change. So the amount of force that's getting put on that object is increasing. Now, we can still calculate the amount of work that's done because the shape that we have here now is a triangle. We have a triangle, so the area of a triangle is 1/2 the base times the height. That's what's being shown here. It's the same thing here. 1/2 the base of this guy, if we were to put it in here, is delta D. That's our change in position. The height is our force that's applied to it. And so at the maximum of this, we apply 2, 4, 6, 8 newtons of force. And so we would substitute in those numbers there. So our change in position is 4.0 meters times the amount of force that we put on it, which is 8 newtons, times the 1/2. So we plug that in. 4 times 8 divided by 2 gives us 16 Newton meters. So 16 Newton meters, which is the same thing as 16 joules, is our final answer after checking the significant digits. So that's how much work we've done. So those are graphs with geometric shapes. Now there's one more thing that's worth talking about. Now this next type of problem is a little bit different because there are no obvious shapes in there to help us predict. And what you're going to notice is that the language behind this particular problem is different as well. So let's check it out. So this one here, here's where our big language shift is. This time it says estimate the work done on by the force represented by the graph. Let me just shrink this down a little bit here so we can see it a little bit better. There we go. So estimate, that's our first thing here. We're not getting an exact number here because you'll notice that our shape here is not a clean and simple shape. We've got this wavy curved line here. Now, what that's telling us is that as force was applied to the object, the amount of force that applied varied. It didn't go up linearly. It sort of ebbed and flowed as the position of this guy changed. So we need to be able to estimate that. Now, there's a couple extra steps that we're going to need to do here. Sort of the way that we're going to teach you to go about it is we are going to count the number of squares underneath the graph. Remember, we're still looking for the area underneath the curve. And so we're going to count the number of squares. So here, 1, 2, 3, 4, 5, 6. There's 6 in that one. When we get to one like this, let me just get rid of all that stuff there. When we get to one like this, whoopsies. When we get to one like this, so this row here had 6. When we get to something like this, with this box here, where the line cuts through the middle, we're either going to round up and call it 1 full square, or we're going to round down and call it no square. So because there's more than half of this square here that is filled, I'm going to call this 1. And you'll see how it kind of balances out as we go. So here I'm going to count 1, 2, 3, 4, 5, 6. So that's another 6 in that one there. This guy here, there's less than half of that square has space underneath. See that little space that I just shaded? There's less than half of the square that's shaded being under the square. So I'm going to call that 0. 1, 2, 3, 4, 5. Not going to count this one, but I'm going to count 1, 2, 3, 4. That guy has 4. Going to count this guy. 1, 2, 3, 4, 4. Going to count this one. 1, 2, 3, 4. That's also got 4. 1, 2, 3, 4.
1, 2, 3, 4. Those guys both have 4. 1, 2, 3, 4. This guy, I think it's a little bit below half, so I'm not going to count him. I'm going to count 1, 2, 3. So this is 4. This is 3. I'm going to do the same thing here. I'm going to count that one. 1, 2, 3. That one's got 3. I'm not going to count that one, just going to count it 1, going to count it 1, not going to count that one, not going to count that one. So when I tally those all up, that'll give me my estimation for the number of squares that I have. So let me just punch that into my calculator quick here. So I've got 1. I'm just adding those all up. And I came out with 49 squares. Let me do it one more time just to make sure. So I punched them in quickly there. Plus 3, plus 3, plus 4, plus 4, plus 4, plus 4, plus 4, plus 4, plus 5, plus 6, plus 6. 49. So I've got 49 squares. Now, this is close to helping me estimate the area, but I need to know what the area of one of those squares is. All right? And so what we need to do is we need to figure out what the area or the amount of work one of those squares relates to. So this is 5 newtons times 1 newton. This is 1, 2, 3, 4, and then we end up at 5 there. So we go our 5 newtons times our 1 meter. That's 1 square, the area of 1 square. So we get 5 Newton meters or 5 joules. And so now what we're going to do is we are going to take our 5 joules per 1 square and we are going to multiply it by our 49 squares. All right, so 5 joules times 49 squares. You notice that my squares cancel out there. That's not exactly a unit, but those guys cancel out. All right, and what we end up with is 5 times 49, and that gives us 245 joules. Now, this is almost close to being good. However, we still need to consider significant digits. So we've got 1 significant digit here, 2 significant digits here, and so our answer can only be to 1 significant digit. So I need to write this as scientific notation. So I'm going to write it as 2. My 4 here is going to tell me that I can stay rounded down. 2 times 10 to the power of 2, because we go 1, 2 to get over there, joules. So there is my final answer, 2 times 10 to the power of 2 joules. So let's try a couple other examples before I cut you loose. So the first example here, we're going to cruise through. We're going to go really quick. But the second example, I want to pause for one moment and just take a look at how we can use a little bit of critical thinking to help us solve a problem like this. So let's take a look at this first one, this A here. We have a graph that shows on the y-axis our force in newtons and our position, delta D, in meters. That's great. That's exactly what we want. We need to calculate, the question asks for the amount of work done by the forces represented in the two graphs. So this one's really easy. We know that the area of this rectangle, just like this, the area is equal to our length times our width. So all we're going to do on this guy is we're going to say work is equal to force times our change in distance, or our change in position. And so we go ahead and we multiply. It gets up, it's a 15 Newton force multiplied by 12 meters. We throw that into our calculator. 15 times 12 equals 180 Newton meters, or 180 joules. And we're almost done here. We just need to check our significant digits. This has 2 significant digits. This has 2 significant digits. So my final answer needs to have 2 significant digits. So that's equal to 1.8 times 10 to the power of 2 joules. Just like that, there is my answer. Really easy, really straightforward. All we're doing, finding the area underneath that curve. All right, so let's do one more here. This one is a little bit trickier, and I kind of like this kind of problem. this problem's kind of fun to me. What we've got here is we have another graph. Force is on our y-axis. Position is on our x-axis. All right? We're doing good so far. Everything looks great, except we have this weird line. We notice that the force is increasing over the first little bit of distance. At that position 15, where it goes from its starting point to 15 meters, the amount of force jumps instantaneously. It's this sharp jump in force. And then slowly the amount of force decreases until position is at a positive 40, is at 40 meters. Now, in order to solve a problem like this, we need to find the area underneath. So we could estimate it by counting the number of squares. However, what we also see here is with just a little bit of thinking, we can actually create this into two triangles. Now, triangles are easy to solve, and we can do this with any shape, whether it be a rectangle or something along that. One of the practice questions has a combination of both of them in there. But we can do this with any one. So I'm going to call this one triangle 1 and call that one triangle 2. So what we're going to do is we're going to solve the area for the two different triangles. So the area of triangle 1 is equal to 1/2 our base times our height. So our base in this guy is 15. So 1/2, 15 meters. Our height in this guy is 2. Which is in newtons, so 2 newtons. So we plug that into our calculator, and we get, oops, I just opened a new page here. We get 15 times 2 is 30, divided by 2 is 15 Newton meters. All right, so we get 15 Newton meters. We got to get this down to one significant digit, so we would write this as 2 times 10 to the power of 1 Newton meters, or joules. So 2, can you guys still see that? Yeah, you can. 2, let me just bring it up here just a touch. There we go. So that gives us 2 times 10. That gives us, our rounded one is 2 times 10 to the power of 1 joules. So that's for this triangle here. So that triangle's done. Now we need to find the area of triangle 2. So our formula is the same. 1/2 base times height. So let's plug in our information here. 1/2, our base, now this is the change in position. So we're not going to put 40. We're going to put 40 minus 15. That gives us this whole base length here. So 40 minus 15 gives me 25. So my base is 25 meters, and we're going to multiply that by my height, which is my force in newtons, and so that force is 4.0. Oh shoot, I made a mistake there. We'll go back and fix that one. 4.0 newtons. So what we're going to do is we're going to multiply those guys together. All right, so 25 times 4 divided by 2 gives me an answer of 50 Newton meters. We have 2 significant digits and 2 significant digits. So 50 Newton meters is perfect. We can also express that in joules. So we get 50 joules. Now that's great. Now the mistake I made over here, that this wasn't just 2 newtons. This is 2.0 newtons. So this is now 2 significant digits, and I can keep it as 15 Newton meters. So my new answer for this one is now 15 joules. So we've now calculated the area of this triangle here, and now we've calculated the area of this triangle here. The final thing we need to do is just add them together. 50 joules plus 15 joules gives us 65 joules. And so the amount of work that's been done on this object is 65 joules. Now we can do this with complex shapes. And so that's what you're going to practice when we get to the problems here. So that's been our conversation about work for today. We'll pick this up in the next lesson when we talk about scalar versus vector quantities.